Turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
Questions. Research.
technology. Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to The Naked Scientists. This is the show that brings you the biggest breakthroughs in science, technology and medicine. I'm Chris Smith. And coming up, Operation Ouch's Chris Van Tilliken tells us why he's tackling obesity in his Christmas lectures this year. Also, how radioactivity encased in diamonds can make safe batteries, one spin-off of which is that they can potentially last for thousands of years. How's that for timekeeping? And they weren't alien spacecraft after all, but what are the dark comets that space scientists are now documenting?
From Cambridge University's Institute of Continuing Education, this is The Naked Scientists.
First this week, the UK's Chief Medical Officer Chris Whitty has used his annual report to bear down heavily on obesity. He's advocating for a stiff levy on junk food to tackle both childhood obesity and, he says, worklessness. The move, which has been dubbed a fat tax by the British press, comes as the broadcaster, doctor and author Chris Van Tilliken prepares to deliver the 2024 Royal Institution Christmas lectures on this very topic. So I caught up with him during his rehearsals for the scientific showpiece.
Lecture one is from your mouth hole to your bum hole, the tube, the mechanical and chemical destruction of food and its absorption. Lecture two is how we literally use the elements in our food to produce energy and as construction material. And lecture three is about the processing. And we're building toward trying to build a deep understanding of how processing affects our physiology and how we've gone from the food system being a miracle that feeds people better than at any other time in the Earth's history to simultaneously being the leading cause of early death for humans and animals. So poor diet is now a very, very serious cause of disease. And it's also a source of real problems for the planet. Carbon emissions, agrochemical inputs, loss of biodiversity, extinction, and so on and so on.
This was really the thrust of ultra-processed food and ultra-processed people, wasn't it? Your book, which was excellent, by the way. I really enjoyed going through it. And it's kind of its moment, isn't it? Now's the time we need to be talking about this, because it's almost like we've forgotten what food is for and where it comes from, because home economics has been ditched across the curriculum in many, many countries. And as you say, the world is malnourished, not undernourished.
That's a very good way of putting it. Although I disagree that now is the moment. In fact, the moment was 10 years ago or 20 years ago or 30 years ago. So in 1990, 5% of children in the UK at the age of 10 were living with obesity, which is an unacceptably high number. I mean, having an integer percentage of children living with diet-related disease is not tolerable. We've let that grow and expand so that a quarter of children now leave primary school living with obesity, roughly a quarter. So doing nothing isn't an option. And the source of the problem, and this is extremely widely agreed upon now, I don't think anyone credible could disagree, that problems like obesity have at their heart commercial incentives. They are caused by commercial interests in the same way that the pandemic of lung disease was caused by commercial interests. And so they need similar kind of policy approaches and regulation.
How are you going to make this digestible for kids? Because that's really who the lectures are targeted at, isn't it? It's young learners, people you want to inspire to become the next generation of people who will change things.
The Royal Institution is the first time I have really spoken directly to a young audience in public about food. So weirdly, on Operation Ouch, which we've been making now for well over a decade, we don't do it, and we don't do it for a good reason, which is because the food on kids' plates, they don't get to choose. And telling kids what safe and healthy food is, it feels very unjust when they may not be able to access or afford that food. And when other food is marketed to them as being healthy, when it probably isn't, or definitely isn't. And so I think we've got two concerns. The primary one is that kids leave these lectures feeling empowered, feeling knowledgeable, not feeling anxious, and with an increased level of understanding and a reduced level of shame and stigma. There's a separate, quite discrete concern about eating disorders. And so as a result, the Royal Institution, and I do this generally, but they've taken it really to another level, They have very specifically engaged with eating disorders experts, clinicians, academics, to make sure that we are going to reduce the risk of eating disorders with the lectures, not increase them. It's very important, particularly that kids who are, well on their way to becoming grown-ups, this is an audience of 11 to 17-year-olds, that they do understand how the food system harms their bodies and the planet, and the kind of changes we need to be looking for. And that's scientific, right? I mean, the discipline of the Royal Institution is to use science as the tool, to say that good science is truly independent, good science is conducted without external influence, and the science tells us about the harms, the science tells us about the origin of the harms, and the science leads us toward the kind of policy solutions.
One of the things that defines the Royal Institution Christmas lectures, though, has got to be the demos and the interactive nature of it. So what's up your sleeve to turn food into something which can do that?
I guess at the heart of the big question about food is it's an energy source. So it's full of energy, and you can release that energy in all kinds of interesting ways involving strong acid, explosions, flames, and general fun RI demo dangerousness. The discipline of demonstrations makes these unlike any other lectures I've ever given. And I think all the lecturers say this, that even if you're a kids communicator, you're still pretty used to using your words. And so being forced to show things is a massive headache in a way, but once you do it, it's really, really good. And my favorite example, in lecture 2, we will explain the very significant difference between the way an internal combustion engine takes hydrocarbon fuel in and produces energy and the way your body does it. To do that, we have to turn the audience into subatomic particles. We have to inflate a reservoir with protons. We have to create a lightning bolt, and we have to create all the chemical intermediates that transmit and carry energy around the cell. The shorthand for this is called oxidative phosphorylation. And in order to explain this to kids, I've had to phone a number of professors of biochemistry. So as the RI team, we've got young experts who are working with me. I think we would all say that we have understood this process now in a level of detail that we never grasped. I definitely understand it better now than I did during my PhD. Some people have done biochem degrees and they're like, oh, right, yeah, no, I never quite got elements of it until now. It's an Einstein quote, isn't it? If you really want to, I mean, it's what everyone says, if you want to understand something properly, try and explain it to an 11-year-old. And if you can't, you probably don't understand it yourself.
One of the things that characterise a lot of the things, people always phone in programmes I'm on and they always want to talk about flatulence. So sorry to lower the tone, but will farts feature? That has to be part and parcel of any lectures about food.
Farts feature, burps feature. We're going to do a demonstration that illustrates, I think, very, very clearly why you must not set your farts on fire. We're going to explain, I'm going to leave this as a spoiler, are farts particles of poo? Because if farts are particles of poo, this is a huge problem, right? Because surgeons farting during operations, which need sterile conditions, might be causing wound infections. So we will be discussing farts in more detail than I think has ever been done before in public. I think I can say that.
Chris Van Tullochen there. And if you want to catch Chris, the 2024 Christmas lectures from the Royal Institution will be on BBC 4 on the 29th, the 30th and the 31st of December at 9 p.m. They'll also be available on iPlayer from the 29th of December. British scientists have created the world's first carbon-14 diamond-based battery. By capturing the fast-moving electrons that are given off when radioactive carbon-14 atoms decay, none of which can actually escape from their hard diamond casing, the technology promises to provide power to devices at low levels for potentially thousands of years. Here's its creator, Tom Scott, who's at the University of Bristol.
Instead of using nuclear fission, for example, which is what we do in a reactor to heat water, to create steam and drive a turbine, and in doing so generate electricity, we're actually generating electricity directly through radioactive decay. And so what we've developed effectively is a cousin to the solar panel, except instead of needing sunlight to generate the electricity from the panel, we're actually using radiation. And what we're actually doing is we're embedding inside the voltaic the radioactive material such that the energy is produced and converted inside a single device. And that makes it very efficient.
So what materials are you using, and what's the origin of the radioactivity in the first instance?
The radioactivity that we've been using in this first device is an isotope of carbon called carbon-14. And actually, carbon-14 is naturally created in the upper atmosphere. The presence of it means that we can do things like carbon dating archaeological finds. But in our case, because it's radioactive, when it decays, it releases a beta particle, which we then convert into a trickle of electricity in our devices. Now, our devices are actually made from diamond, which is a phase of carbon, which is really very hard. It's actually one of the hardest natural substances on the planet. And what we do is we grow diamond from a gas plasma that we create, and we incorporate into the diamond the radioactive carbon. So all we're doing is we're substituting non-radioactive carbon in the diamond for radioactive carbon. Because the diamond's really dense and it's really hard, it forms a really, really good cage. So that means that we can convert the radiation energy into electricity, but also that the radioactivity doesn't escape from the device, which makes it intrinsically safe.
So you've got the radioactive source, which is the atoms of carbon-14 inside the diamond. What are they hitting in order to produce the electricity and then for you to tap off the electricity, if that's all going on inside a diamond?
Yeah, so we create a special structure within the diamond. It's actually what we call a diode structure. So that means that any electrons that we create within the device will flow in a single direction out of the device, which we can then connect to a working circuit. So that might be a transmitter, it might be some sensors that we can make some readings with. A beta particle actually you can think of as being an extremely high energy electron. And so when that fires out into the diamond structure, you can think of it as bouncing its way through the structure. And with each sort of collision it makes with another carbon atom, energy is dissipated into the structure of diamond as essentially like a cascade or a shower of electrons. And it's that shower of electrons, which is the electricity, which is then flowing out of the device. I like to describe it as being something a bit like a sandwich. In our device, we have layers of diamond, which is not radioactive. And then we have a layer which is radioactive. And then we have another layer, which is not radioactive again, but it's been doped in order to help with the flow of the electrons in one direction out of the device. So a bit like a ham sandwich, where the ham layer is the bit for our diamonds, which is the radioactive bit.
How much energy comes out at what sort of voltages, and how long will this last?
So we're talking about devices which are never going to power cars or trains. We're talking about devices which constantly trickle out a tiny amount of power, and we're talking sort of microamps at about 2 volts, but it will do so for a very long period of time. So the half-life of carbon-14 is about 5,300 years. And that means that with our devices, they will have hit half power output over that period of time. So in terms of human timescales, we're talking about a forever device, but in terms of geological timescales, we're talking about a device which would continue to produce power for several thousand years.
What do you think you can do with it? When you know you've got something at 2 volts with a few microamps, what sort of things could that power?
Typically, we're looking at device applications where we can use that trickle of power, either because it's at sufficient level, it can continually power a very low power consumption activity. So that could be something like you could think of as a pacemaker potentially. But for most of the device applications that we've already done sort of a prototype for, we're trickle charging a very low leakage capacitor, which is storing the electrical energy. And when that capacitor over a period of time gets full, it then will discharge itself into a working circuit, which might contain sensors or transmitters, for example. And so very much we see these devices as working in what we call a chirp mode. So every so often, a device will chirp some information or it will make a reading and then send that information. And it will do that for very long periods of time. So potentially very useful in things like environmental monitoring in very extreme places where it's either very hot or very cold, or maybe, for example, at the bottom of the sea, or even at the bottom of an oil and gas well, or where we're storing carbon dioxide. But also lots of applications in space where it can go from very hot to very cold quickly. And you also need a device which can withstand the sort of solar radiation that's much stronger out beyond these protective bounds of the atmosphere. Really, we're not looking to replace or supplant the standard lithium ion battery. What we're trying to do is provide a power source which is very good across extreme environments and also in very remote locations where it would be very expensive or potentially dangerous to try and go and replace a chemical battery.
Absolutely amazing. Tom Scott from the University of Bristol there. And a bit later on, actually, talking of nuclear, James Titko will be taking on one of your questions about a similar topic. So stay tuned for that.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions.
This is the Naked Scientists podcast with me, Chris Smith. Still to come, dark comets. No, they're not alien spacecraft as we first thought, but instead unusual celestial bodies making strange movements. But first, to a new genetic analysis which has helped to pinpoint the period when modern humans first began to mix and interbreed with Neanderthals, which were a parallel species closely resembling but genetically distinct from us that lived in Europe for hundreds of thousands of years before disappearing about 40,000 years ago. Now, we know the two groups interbred once more modern humans arrived in Europe from Africa because scientists have assembled the Neanderthal genome from archaeological remains, and we can still detect Neanderthal DNA sequences in our own population today. But now scientists in the US and Europe have gone a step further to identify more precisely when. They've done it by looking at how ancient and modern DNA samples have been affected by a process called recombination, which happens when eggs and sperm are made. To increase genetic diversity, the body randomly switches equivalent chunks of DNA between the two pairs of each of our chromosomes. This means that genes that sit next to each other on the chromosome tend to be passed on together like this, so you can follow them, a bit like genetic breadcrumbs. But as more time passes, they get progressively more fragmented as more recombination events slowly split them up with each new generation. Hey presto, a genetic clock. And what it shows is that Neanderthals and modern humans overlapped and interbred for potentially 5,000 years. Here's the discoverer, Arev Sumersha.
One thing that was always debated was if our ancestors mixed with Neanderthals or not. And we already have an answer to that question due to the first genome of a Neanderthal that was sequenced in 2010. And the answer is yes. So all humans outside of Africa living today, they do carry some DNA from Neanderthals. And we have a broad idea when this might have happened and where, but we would like to understand better the interactions at that time between the different human groups, being modern humans and Neanderthals.
How can we get at the answer to that question, given it was so long ago?
What we use to understand it better is what we call ancient DNA. This has been a field that is growing really fast over the last 10-15 years. And what it means is that when we are excavating an archaeological site, if we find human remains, being tooth or bones, or even actually today we can do with sediments, we can extract DNA from the individuals that lived in the past using these remains. And this would allow us to jump back in time and see some of the genetic aspects of the groups that these individuals belong to.
And how are you trying to then get the answer to that question, which is when and where that mixing most likely happened?
When our cells are dividing, there's something called recombination. And because of this, there's shuffling of genetic information on our genome. Imagine if you would have a parent that is a modern human and a parent which is a Neanderthal. You would have one set of chromosomes from one individual, one parent, and the other from the other parent. And what recombination does would be then breaking down these parts. So the chromosome that came from the Neanderthal parent would then break into pieces. So this happens once in each generation, right? So we use this information, the length of this Neanderthal DNA in the genome of us, to be able to calculate how much time, so how many generations must have passed since we had this Neanderthal ancestor. And using this information, we can actually estimate the timing of this mixing event to where we think it is probably Middle East, but we do not have any direct evidence to suggest.
Right, so this technique you're using, this recombination, basically you're saying, well, if I swap bits of genetic material from the chromosome of one parent to the chromosome of the other, which is what happens when we make eggs and sperm, isn't it? And that as this happens more with subsequent generations, the bits which are all Neanderthal slowly get separated out more and more and more, so they dilute out. So you can wind the clock back to see where that first must have happened. So what time point then does that lead you towards when this probably began to really happen first?
What we did in my study is that because our individuals are so old, that they're older than 45,000 years, we find that the Neanderthal DNA in their genomes is in the form of really long segments, which we can detect very well and very precisely. And we use those to identify how many generations have passed since mixing and when these individuals lived. And that was about 80 generations. We were able to then multiply this time with the generation time of humans, which is 29 years, and estimate when the mixing event happened, and that was about 45 to 49,000 years before now.
Can you also get at another important question that seems to come up a lot? Because we know that Neanderthals subsequently disappeared, but we also therefore know that there was a period of coexistence when we overlapped. And we don't know how long that was, though. Does this give us any clues about that question too?
It does in a way. We know that Neanderthals disappeared about 40,000 years ago. They were already in Eurasia when our ancestors left Africa. So they must have overlapped probably at least 10,000 years. We don't exactly know when modern humans migrated out from Africa, but our results say this must have happened at least 49,000 years ago.
If you look at the genes that we still see in us today, are there any interesting patterns there? Are there any genes that seem to be there far more often and argue that they do something good for us, and therefore interbreeding with Neanderthals tooled us up genetically to make us more successful? And then the flip side, are there any genes which you know are very prominent in Neanderthal populations that just completely disappear once this overlap and this admixture of the mixing of the genes between the two different species happens, which would argue that perhaps some Neanderthal genes were bad for us and disappeared?
Definitely, we do see that. So there are regions in the genome of us today that we do not see in any human living today, any Neanderthal segment or DNA in these regions. We call them the deserts, so the Neanderthal deserts, because there's nothing there from Neanderthals. On the X chromosome, it is definitely depleted from Neanderthal genes. And this could mean that negative selection removed the Neanderthal DNA from this region in human groups. And it could well indicate that this was because of some kind of incompatibility in mating. Maybe people who had higher Neanderthal genes on the X chromosome were not able to reproduce as well as those that didn't have. It could indicate that maybe there was some sort of unsuccessful mating between these individuals. There are also other regions in our genome that are high in Neanderthal genes, possibly beneficial for us. And these are often related to immune system. So we could think that because our ancestors left Africa much later than Neanderthals evolved in Europe, probably Neanderthals were better adapted to the conditions in Eurasia and also to diseases. So perhaps when they mixed with our ancestors, the genes that provided them protection from some disease were beneficial for our ancestors, and hence they were positively selected.
Arev Simersha from the Max Planck Institute for Evolutionary Anthropology. She just published that work in the journal Nature. In 2017, the first object we've been able to observe visiting our solar system from outer space first tumbled into view. Because of its peculiar cigar-like shape and the fact that it was moving in an odd, extremely rapid way, it ignited a media frenzy with speculation that it might in fact be an alien spaceship. Further investigation eventually concluded that it indeed was an alien, in so much as it was from somewhere outside our own solar system, but it was nevertheless a lump of rock, and somewhere between an asteroid and a comet. Space scientists called it Oumuamua, meaning a messenger from afar in Hawaiian, which was a nod to where the telescope used to discover it was located. Now, scientists have documented 7 more new so-called dark comets, which are not from outside the solar system, but they do still show strange patterns of movements. It also comes in the same week that a team from MIT have described 100 small asteroids, some just 10 metres across, in our solar system's main belt with the James Webb Space Telescope. Here, to make sense of it all for us, is David Rothery, who's Professor of Planetary Geosciences at the Open University.
There are asteroid-like bodies which have been seen to move in trajectories which are not quite the orbits, but they should have. The orbital path of anything around the sun is basically an ellipse if it's within the solar system, and there's some slight perturbations to orbital motion because of how sunlight is reflected and absorbed heat is re-radiated. But we have about 14 now objects which are being called dark comets, which is a bit of a misnomer, but you'll see why they're called comets. And the explanation for these non-gravitational accelerations or perturbations in the trajectory is that they must be degassing. Gases are escaping and flinging away some dust, and the reaction against the dust being thrown away is what causes the main object's speed and direction to change.
And did they come from our solar system or outside the solar system? Because the original claim, when Oumuamua, the first one that was documented a few years ago now, was written about, people said this was an alien spacecraft because it appeared to be coming from outside the solar system. How did they know that, and where did the rest of them come from?
Yeah, well, the object now known as Oumuamua was discovered when it was screaming through the solar system at far too fast a speed to be orbiting the sun. So for Oumuamua, a few people said, "Oh, it's the alien spaceship from far reaches of our galaxy adjusting its trajectory with reaction rockets or something." But no, it's just, we think, small amounts of degassing. Something from very deep space is going to have ices in it, which when you get close to the sun, the ices will volatilize, sublime, some dust will be thrown up, and the speed and direction of travel will be tweaked ever so slightly. Now, the dark comets are not interstellar objects. They're orbiting the sun. About half of them are near-Earth objects. Their orbits come past the Earth, and others stay out in the main asteroid belt. They're not the same class of body as Oumuamua, but they've got the same phenomenon going on, which is material being thrown off in too small quantities for us to see, but which we can infer because of the way their orbital paths or orbital trajectories are being changed.
I'm slightly disappointed that they're not alien spacecraft. That would be quite intriguing and quite a discovery, wouldn't it? But one of the things that people do speculate in some of the coverage of this is, well, these sorts of objects might be seeding life-giving molecules. So they're not themselves alien, but they might bring life that can take root on various places. Is that sort of over-egging the pudding?
I think it is, Chris. To have volatile substances, and presumably some carbon-rich material, that's the material which you need on a young planet for life to form. But these objects, they're fragments of larger things. But this class of objects we see now crossing the Earth were not there 4.5 billion years ago when the Earth was forming. So it hasn't taught us really anything about delivery of organic materials to the early Earth.
Talking of interesting things that are also out there and occasionally visit the Earth, as in they come and produce fireballs and stuff, those are asteroids that come and rain in on our atmosphere from time to time. There's this other paper which is documenting enormous numbers of small asteroids. And is this right, that they can see something 10 metres across, way beyond the orbit of Mars from Earth? I mean, that's just outstanding astronomy.
Yeah, these are observations by the James Webb Space Telescope, or JWST. It has detected large numbers of what are being called decameter size asteroids. That's 10 meters, or a few tens of meters in size. So there's a lot of 10-meter size material out there, some of which will eventually get onto orbits which intersect with the Earth. But it doesn't mean they're a big threat to the Earth, because objects of these size probably wouldn't get through the atmosphere intact.
What's the importance of the discovery then? Or is this just the James Webb team flexing their astronomical muscles to show, yeah, we can do this. This is why this is a powerful instrument. Look what sort of resolution we can achieve.
I think this is a wonderful bonus discovery. I'm not sure if this was in the plan for JWST, They wanted to look for planets around other stars. They wanted to do deep sky work. And there's wonderful images we see of all kinds of things in deep space. But it just shows that when you get a new wavelength accessible to you in the infrared like JWST with high resolution, no light pollution, no thermal pollution, you're able to do a lot. And the observations to discover this class of bodies and to get the statistics on them so they can learn about the dynamics of the collision and fragmentation process going on. This is all the bonus through staring at primary targets. It just shows that when you build a good instrument, you can do so many more things with it that perhaps you didn't expect.
Thanks very much to David Rothery from the Open University. And now it's time for Question of the Week, where James Titko is answering this question all about nuclear energy.
Hello, Naked Scientists. This is Dave from Hobart, Tasmania. I was wondering if there is any other way to produce electricity from nuclear fission apart from generating steam to turn a generator. Thank you.
Thanks, Dave. I suspect this might be a follow-up from our recent programme on nuclear energy. As you indicate, the way a traditional nuclear power plant works is by splitting apart heavier atoms from the periodic table, usually uranium, and using the heat energy this gives off to boil water, using the steam that's been produced to spin a turbine, eventually converting that kinetic energy into electrical energy. But is this the only way to get energy out of a nuclear reaction? Well, as it happens, there are other methods, and we've happened to cover one in this week's news show. The carbon-14 diamond battery, designed by Professor Tom Scott from the University of Bristol and his colleagues, harnesses energy directly from the decay of radioactive carbon-14 atoms, as he was telling Chris earlier, not from a fission reaction, like you were asking about, Dave. So are there alternative methods of generating energy from nuclear fission specifically? Well, yes, in theory. One way is by directly using the kinetic energy from fission products. Let me explain. In a nuclear reactor, the fission process splits uranium atoms into two lighter fragments moving at high speed and thus possessing a lot of kinetic energy. The fragments are also positively charged because they've been stripped of their electrons. If the nuclear fuel is made really thin, on the order of microns, these fission fragments could escape and interact with an external system, such as an electric field. Attracted to negatively charged electrons, they could transfer their kinetic energy to said electrons crowded on the electrodes, creating the electric field, producing a current. Now, this is a very exotic application with numerous technical challenges to be overcome, the need for ultra-thin and durable nuclear fuel, for example, but it's fascinating nevertheless, and an active area of research along with other experimental methods that are worth keeping an eye on. I hope that's answered your question, Dave. Thanks so much for sending it in. Next time, we'll be answering this question.
Hello, it's Damien from Hathersage in the Peak District in the UK. My question is, if the continents were once all joined up as a supercontinent, what was on the other side of the Earth? Was it all just water?
Thanks, Damien. And across Christmas, Question of the Week's taking a little bit of a break, so you've got slightly longer to think about this one. But if you have an answer, or you have a question of your own you'd like us to delve into in the new year, why not send it in? It's chris@thenakedscientist.com. That's all we have time for in this episode, but do join us on Tuesday when Titans of Science continues with the Nobel Prize-winning biochemist and discoverer of all things proteins, David Baker. The Naked Scientist comes to you from the University of Cambridge's Institute of Continuing Education. It's supported by Rolls-Royce. I'm Chris Smith. Thank you for listening, and until next time, goodbye.